Everybody, today we're going to talk about how to prove convexity for a given set. And I got that problem from wait a second, let me change the thickness. Okay, that should be alright. And I kinda didn't like the color. That's not a good start, but let's see what happens. Stephen Boyd, that's a terrible B. Alright, and convex optimization book. Alright, so 2.11, this is problem 2.11, and this is called, that type of set is called hyperbolic set. So let me change the color and let's look at the problem closer. So for a given x1, x2, so imagine this x1, this x2, right? And then we have these given two constraints. I mean, if you think about it, we can expand it as like that. So basically we have three constraints, and then it should look something like this, right? And then anything right to that given boundary surface. Okay, so this set, it looks convex, of course, but we need to prove it like algebraically. How would we go about doing that? So the hint in the problem given is that one. So let's look at here, and what we can notice is that this is something like generalized version. That's why I say this is like the generalized version of AM GM inequality. What was that? AM arithmetic mean was always greater than equal to geometric mean. This is the geometric mean, right? So okay, and in general, how we would write that, this is arithmetic mean and this is geometric mean, right? So that portion is for two variables, generalized version, right? And because if you think about it, anytime I write something like this, right, in a way, let me write it one more time actually. Instead of writing like that, I could have written theta I xi, alright, and theta I xi, where all the theta I terms are greater than or equal to 0, plus they all sum up to 1, right? So this is, this is like a probability simplex. So alright, that was a long detour. So we need to prove the convexity of this given set. And how do we prove that? Before that, let's define what a convex set is. A set C is convex if the line segment between any 2 points in C lies in C. And so this is annoying, the typo here. Yeah, i.e., a set C is convex if for all x and y in C, right? So imagine you have that set, or you have that type of sets, right? And these are like linear, right? And any point that you choose, if you draw a line, all the points that are on that line should be in the sets. Okay, and it's obvious that this cannot happen for the sets, because here there are some lines that lies outside of the convex sets, outside of the set. So using that definition, let's look at I will present 3 solutions, alright, and I think only the third one, or yes, second one, I got it from the internet, and the other 2 are kind of my solutions, quote unquote. And the third solution is definitely my solution. I think it is correct, but I'm not sure. I will, give some details on that. So, okay, let's look at that. We choose X and Y in given sets, right? So now what we are doing is, again, we're going to use theta, right? So this is X and this is Y to parameterize the lines, right, that lies on the sets, on the set that is defined by the line segment between X and Y, right? We parameterize this, so this is our knob, right? So turning that knob, we go from here to here, right? So this is 0 and then this is 1, and we turn it, right? Something like that. So, and what we want to prove is this. If the answer to that question is yes, then we say that this given set is convex. All right, let's go and deal with it. And I write theta bar because it is annoying to write theta minus 1 all the time, right? So let's look at the condition 1. What was condition 1? Let's remember. Or I think I'm gonna write, something like this. So this is condition 1, this is condition 2, and what's that? This is that one, this specifically, this is condition 3, right? So we will prove 3 conditions. So that one, alright, is that greater than and equal to 0. So using the given terms, alright, we can immediately say that, so this is the average, weighted average nonetheless, of 2 strictly positive numbers, right? And because of that, this is of course positive. And one more thing that I'd like to mention is that although we set the conditions as this, right, these were the conditions, if you think about it, so this is inequality, this is not strict inequality. However, I'm going to ask you a question. Can x1 be 0? If you look at it, this condition, no, x1 cannot be 0 because that inequality wouldn't hold in that case. So we could easily write or change the conditions here, the first and second condition, to that, right? So that is something to keep in mind, right? And alright, but it's not extremely crucial though. Alright, so that one is correct, and let's move on. So this is the condition 2. Again, we basically do the same thing, right? A weighted average of 2 strictly positive numbers, or let's say it is not even strictly positive, right? And weighted average of 2 non-negative numbers will be a non-negative number here, as we can see, right? So let's look at the final condition, condition 3, and that one will be interesting. So what was condition, what was the set condition? Let's remember. So these three conditions, right? And we have the first condition proved, the second, and now we will look at the third one. What is that? So you give me a vector like with 2 points basically, and then I'm gonna multiply them, right? If the answer is greater than or equal to 1, then I will say that condition is satisfied. So I will be looking at this. Alright, so this is, let's call it actually Z1, right? Z1, Z2. We can write it with bold Z. This is x1, x2 plus theta bar y1, y2. Okay, so we want to prove if Z for this theta values will take values that are in the set S1. Okay, let's look at that. Z2, let's call that. And so we're going to investigate that. Let's expand this. Let's expand it. And 1, 2, 3, 4. We will have 4 terms. I'm just writing them here, alright? And now there's a trick that we can have. So looking at the second and the third terms, alright? I am arranging them in this fashion. So the reason I introduced 2, I'm basically multiplying it 2 by and then dividing it by 2, so same, like nothing changed. However, the reason I wanted to do that, now this term, if you look at it, let's call it term 1 and term 2. This is the average, like arithmetic mean, AM of the given 2 terms, right? So now you may say, yeah, I think we are gonna use like AM-GM inequality, and then yes, you're right. X1, Y2, Y1, X2, alright? So those given terms, don't even look at it, just call alpha 1 or alpha 2, alright, if you feel better about it. And so this is the AM, and this is the GM, alright? So I am also arranging them in a way that the inequality is useful. So let's go and continue using these given inequalities. Where do we get those inequalities? This is the third condition. This is the third condition from the S1 sets, right? And we can say that, like what I'm saying is that there is one number that is greater than or equal to 1, and alpha 2 is also greater than or equal to 1. So you would know that like product of them would be greater than or equal to 1. So this is basically what we are doing. And then we can write that. So since that expression is greater than or equal to 1, right? So this expression is greater than or equal to 1, and when we take the square root of it, it will be greater than or equal to 1. And this is actually interesting. Why? Because so this is x, and then this is square root of x. This is 1, and this is 1, right? So square root is such an interesting function. Let me try to plot it. This is x function, right? So if this term was something, I don't know, 0.8, or let's call 0.81, right? And when we take the square root of it, what would I get? I would get 0.9. But wait a sec, this one is greater than that term, right? So this is exactly what's going on here. And the reason why this term 1 is special, because after 1, after 1, x takes, after 1, basically what I'm trying to say is this, for all x that is greater than or equal to 1, right? So we are basically using that expression. And okay, I mean that was like a simple thing to explain, but alright, so now that's, let me even clean this up. Now that we have this, right? So we can say that that term is greater than or equal to 1, right? Because that term is am, right? That term is greater than this term, and then this term is greater than 1. So that term is bound to be greater than or equal to 1. All right, now we know something that we didn't know, and this is greater than or equal to 1. This is greater than or equal to 1. Why? Because this is the third condition from the definition of set S1, and that term is also greater than or equal to 1. Again, greater than or equal to 1, greater than or equal to 1. So, you know what? Let's just say that, let's be very pessimistic, all right? I mean, of course, we should be very optimistic because this is 2025, and then, you know, a lot of good things will happen, or bad things, who knows, but let's keep a positive mind about it. And alright, after that long ADHD session, so let's be pessimistic and use the worst values, right? The smallest values that they can take, right? Because we are trying to prove that term being greater than or equal to 1, right? And there are some terms that would take some values, like ranging from, let's say, A to B. And let's think about the worst thing that expression can take, all right? What is that? How would you do that? I'm saying the worst thing that this value can take is 1. Same for this and same for this, right? We can even simplify it if we want, and let's call it alpha 1, alpha 2, and then alpha 3. And then I'm saying, and let's give them, since we have this, let's look at the situation when alpha I is 1, right? And what would that give us? It would give us this. And oh my god, this is very interesting. Why? Because this is basically square of what? And a quadratic term, alpha theta plus theta bar squared, right? So, and on top of that, we also know theta plus theta bar is 1. So this is 1 squared greater than or equal to 1, and this is 1 greater than or equal to 1, and yeah, this checks out, right? All right, so let's remember what we did. We did a lot of good things today, and we have the condition 1, right? We prove that. We have the condition 2. Actually, wait a sec. Yeah, okay. Condition 2. And then we also have the condition 3. We prove all of them, right? So, any value that you give me in the sets x and then y, let's call them, and all the values, all those points, right, and are also in the sets, right? So that is the definition of convexity. So after that we can say S1 is convex. All right, let's look at the second solution. And let's actually, you know what, let's try to see our solution, and let me try to fit it in one page. Yes, that is it. Let me get rid of all those stuff. Alright, this is what we did now. So this is the solution, right? This part is the solution 1, and let's look at the second solution, or second method of proving the convexity of given sets. So again, the starting point is same. You give me an x and then y, like 2 points, and then I will have a line segment, and then I will look at all the points that are on that line segment, and I'm gonna look if they are also in the sets S1. If that is the case, then convexity is proved. So condition, this is so annoying, like having typos. Condition and condition 2 can be checked as given in solution 1. All right. So what I'm saying is that we have three conditions: condition 1, condition 2, and condition 3. And condition 1 and condition 2, we're gonna prove the same way. What were they? This is C1, this is C2, right? And what was C3? Was this. We're gonna look at this now. And that one was the, if you think about it, kinda the part that took longer. So that is the solution that Stephen Boyd convex optimization book offered. And so there are two cases actually that is going to be kinda challenging for me to explain it. Let me try to talk about something. This is x1, this is x2. All right, let's change the colors. Of course, I'm, exaggerating the plots, but it is something like this, right? This is the set S1, and so what I'm trying to say is that, let me get another color. These are linear lines, okay? So there are two possibilities that can happen. If you look at a set like this, what are those? Like x and y, like given 2 points, right? Given 2 points. So let's say this is x, right? And y is anywhere here. Let's say that is the case, right? And of course you can also say the following: that point can be x, right? Just give me a point, right? This is x, and I can give you, or if y is located here, then this is one of the cases that can happen, all right? Of course you can change like x and y, right? Instead of x we could also say y, and then imagine x is in this set, right? For example. So why this is important? What's the significance of that? If that is the case, if the given 2 points have the, actually before even saying that, there are two cases that can happen. This is case 1. What is that case? And you give me a point, and then another point, like you're gonna give me 2 points, and in case 1, one of those points is here, and other point is located somewhere here, right? Of course this goes to infinity, right? This is case 1, but you can also say, hey, I mean, it can also take values here, right? So this is x, and then y can take values here, and I will say yes, that's correct. And this is what we will call case 2, right? So if that is the case, if y is located here, this is case 1, okay. And then if y is not located here, right? If y is located somewhere here, then this is case 2. And let's look at what would happen if we had case 1, all right? So what I'm trying to say is that you give me 2 points, x and y, and if, actually, wait a second, was it x or x and y? And then let's remember, this is actually a vector, right? 2-dimensional. If I write something like this, if I can write something like that, what would happen? Let's try to understand. And y1 minus x1 times y2 minus x2. This is positive, and then this will be positive, right? Okay, this is like for example. And one thing that would result from that relationship. I'm not even saying inequality, by the way. This is a strange beast, right? And sorry I called you beast, but this is a relationship. So this is pointwise inequality. So y1, let me try to write it in explicitly. That means y1 is great. Let's change the y1 greater than equal to x1, y2 greater than equal to x2, right? So this is defined in another context is what I'm saying, or this is not like, for example, matrix positive definiteness type of operator. Okay, so now we can also say that looking at the, I mean, it will be kind of like a geometric way of thinking, but if that was the case, right, if given x, y, like given 2 points satisfy that condition, this is x, right, this is x, and this is y, this is y, and if I have a line like this, all the points will be in that set. That is not even a question, right? Okay, so we could easily say that. But now we will also look at the second condition. What is that? If we don't have that type of relationship, right? Like, for example, what does that mean? That means, I'm given as an example, like I don't want to write all the combinations, right? So if that is the case, and let's look at the implications. y1 minus x1 and y2 minus x2. So y1 is greater than x1, so that means this is positive. Okay, and y2 is actually less than or equal to x2, so that means this is minus, negative, and then this whole expression is negative. Okay, so we will use that now, right? And yeah, this is the case 1, and I wrote something like this. Again, this is something that we know what that is. Right. Yeah, I said that means this. Okay, so of course, again, like instead of writing that, I could also write y1, y2, x1, x2, right? So like I don't need to write all the combinations. We can kind of get it from generalizing. So using this plus the given conditions, derived from the set definition, now we will look at this expression if that is the case. And yeah, of course that is the case. From I mean, I think that's obvious, right? Why? Because so I am taking the weighted average of x1 and y1, right? And x1 is greater than y1, right? And x1 is greater than y1. So the lowest value that, we have the knob of theta, right? The lowest value that this expression can take is y1 already. So that is satisfied. I mean, I showed it for the first term, right? And so hence we can write something like this. So that is it. This is for the third condition. So let's look at the second case, where we actually don't have that type of relationship, and that also implies this plus. So now we need to use this plus the conditions. What are those conditions? Let me even write them explicitly. This is for x1, x2, and then we have y1, y2, y1, and y2. Let me even write something. Can I fit it here? x1 greater than y1, x2 less than equal to y2. So there are 3, 6, 8. There are 8 inequalities, alright? And by using them, we need to prove this. Actually, this is a literal algebra problem. Let me kind of clean this space. Alright. And let's look at if that is the case. Again, we start from the beginning. Alright. So this is basically z1 and z2. The multiplication of the first and second term. And then we're expanding. And yeah, that part was the annoying part actually. It is not easy to see, and then that's why I kinda like, that is the reason why I'm making this video, because I look at the book when I was studying convex optimization and I saw this solution, and then I'm like, going from here to here is not obvious. Alright? Like, that would take some derivation. I mean, that is a great solution, by the way. Like, I really like the logic. But I told myself, you know what, that is a kind of contrary way of thinking. And then, yeah, I look at how would I prove, and then like stuff like that. What would I don't know, a mathematician would do. I'm not a mathematician, but I pretend to be. So that wasn't obvious to me. That explanation, like that derivation, actually going from here to here. And I mean, yeah, when we know it, okay, we can derive and then prove the like this expression actually equals to this expression. We can prove it, of course, but like no one would say, you know what, let's express it in that way, and then okay, now use it something that we can, you know, derive from the given inequalities. That wasn't obvious to me, and then that's why I look at other solutions. And after that one, I will also show another solution, but that was a long detour. So let me continue and complete the second solution. So we are going from here to here, and then I'm gonna write, this is, let's say, easy to see. You know, in the books, they will sometimes say, I feel like they are throwing. And yeah, going from here to here, and this expression is equal to this expression. I mean, yeah, they are equal, but why would you even go there, you know? Anyway, that was my... Okay, so we have that, and what do we see? Since we have this expression, like that term being strictly negative, right? That term is strictly negative. This term is positive, and we have another negative thing. So negative, negative, and then this is positive. So this expression is positive. And what do we see? This is greater than or equal to 1, this is greater than or equal to 1, and this is basically weighted average. So this expression is greater than or equal to 1, and then we are adding to that expression something positive. So whole expression will be greater than or equal to 1, right? And yeah, this is basically what like this part is basically explaining what I just said. And that part, all right, let's say that is also true. So we already knew the condition 1 and condition 2, and by using that logic argument, we prove the condition 3 also holds, and the given set, the S1 is convex. We prove that, right? So, whoa, isn't it nice? I think it's nice. So let's look at the solution 3. That is, I don't want to brag about it, but this is a quote-unquote my solution. And you might even say that, wait a sec, this is like literally, I mean, you were complaining about that. Wait a sec, where is it? You were complaining about this derivation, and do you think this is obvious? You know what, I will say it is kind of obvious. Why? Because like this is a bilinear expression, right? And you could say there must be a STP relaxation, or maybe there must be a like literally STP equivalent way of expressing those constraints, right? And this is not extremely you know, I mean, if you are kind of familiar with STPs, and why not? Like, this is something that you can think of, I think. I mean, I thought it, so it's like anyone can do, in my opinion. I'm not Einstein, so let's look at this. These are the conditions, and I'm saying these conditions are, or we can arrange them in a way that these conditions can be expressed in that form. And look how cute it is. You know, like, this is a very compact way of writing it, in my opinion. So what I'm saying is that why, first of all, let's answer the question, why this is the case. And what is this? This is matrix positive definiteness, right? Easily from that derivation, from that expression, this condition is equal to the given set of conditions. What is that? Let's use in Sylvester criterion, I think it was the name, and x1 is positive definite, and then 2 by 2 matrix is positive definite, and how the determinant of that one must be positive, but this is just 1 by 1 matrix, so determinant is that itself, and determinant of 2 by 2, like basically I'm writing x1 x2 minus 1 must be positive, right? And for example, if that was like 3 by 3, we would also look at the 3 by 3 determinants, right? And if that was n by n, and then we would go and then look at, 1 by 1 determinant, 2 by 2 determinant, n by n determinants must be positive, right? Something like this. Okay. And so it all comes from that, but let's look at it specifically for this problem. We can write again x1 positive, and I didn't want to even write x1 minus x2, but I wrote it actually now. Okay, so x1 is positive, right? What would that cause to? That also makes x2 being positive, right? We could also write something like this. So hence these expressions, like these constraints, can be written in that way. And if you don't believe me, hey, maybe you're, this is your conjecture, maybe how do you know this is correct? And I will say, this is not me saying it, this is Dr. Fauci, Stephen Boyd is saying it. So positive semi-definite con in S2 is symmetric matrices and set of symmetric matrices, and this is S2 symmetric matrices, this is S2 plus symmetric plus positive semi-definite matrices, this is S2 plus symmetric and positive definite matrices. And okay, so we have that, and again this is positive semi-definite, since there's only one plus sign here, and that expression can be written that way. Make sense? Okay, so look at it. This is if and only if. Alright. Yeah, I plotted. So what is this? This is all the points, like this is x1 and x2. Right? I'm looking at all the points. I need to discrete that, so I have finite. My resolution cannot go to like very low values and then, or high values, and it's limited. I'm looking at the points, and I am looking at if they satisfy the given constraints. If that is the case, yeah, I put a dot. And here I'm looking at the points, and if they satisfy this condition, right, to see if these conditions would correspond to that condition. Yeah, and then this is the MATLAB code that corresponds to that. And then let's look at the general version of the given problem. Again, this is a Stephen Boyd 2.11 problem, Stephen Boyd convex optimization problem. So let's look at it. General version of the problem. So prove the convexity of that one. Again, we are not writing that. Instead, we are writing right. We are now looking at this problem. This is called hyperbolic set, and then this is a generalized version of the problem. Now, this generalized version of GM inequality will be very useful, right? Because if you think about it, this is not easy. Like this is by no means easy problem. It's not straightforward. Like seriously, and I mean, if you are like crazy good at not geometry, like algebra, okay, maybe that one might be like a straightforward problem for you. But so, first of all, if all the xi terms are positive and all the yi terms are positive, then weighted averages of them, would be also, let's call them zi, would be positive, like not definitely positive, or at least like non-negative, we would say that. So the first n condition, we're just proving that using that argument. And let's look at n plus 1 condition. What was that? So this is it, right? Instead of xi, so I need to look at this if that is the case, right? But what is zi? Zi is weighted average. I'm sorry, not derivation. I'm kind of tired. So that expression is greater than or equal to 1, right? We need to prove that if that's the case. Again, theta and then theta bar, they sum up to 1, right? And this is what we have. And we're going to do simple derivations. First of all, we will use that, right? So again, we can change it if that is kind of hard for you to see, and to xi and then yi, right? This xi and then yi. So what I'm saying is that I can put theta here and then theta bar here. Basically, this is effectively what I'm doing, right? And using the generalized version of GM inequality. But again, this is inequality. I'm saying that this expression is greater than and equal to that expression. But what was the point of all this? I mean, we are all trying to get our PhDs. I mean that's the main goal, but for this specific problem, we are trying to prove if that expression is greater than or equal to 1, right? We are trying to prove that. So I'm saying that expression is greater than and equal to another expression, and then I will look at if that expression is greater than or equal to 1. If that is the case, then I would know that, yeah, this inequality holds, right? So now I am investigating that. I'm like a detective now, right? I'm investigating if that expression is greater than or equal to 1. So again, this is like algebraic step, some simple manipulation. I'm just writing it that way, right? I'm hoping that is obvious. I mean, if we have that, right, let's imagine let me even write alpha and then beta, alpha, and then beta. All right, so I can write this, and then I can write that, and then I can write okay. So this is the derivation, like this is the algebraic step that we took, and then I'm gonna write it as, yeah, I mean, if that is not the obvious step for you, just think about it for like some time and then convince yourself that is the case. All right, that's like seriously, that should, I mean, maybe in the whole, like, that might look scary for a second, but if you think about it, that's like a really simple algebraic manipulation, right? So okay, I don't want to be like annoying about that, but yeah, just sleep on it if you need to, and then it will make sense. I promise you that. So this is given, like we got this from the set definition. Again, we got this from the set definition, and what I'm saying is that at the end we have these expressions, right? So let's look at, this is term 1 and then this is term 2, let's call it. And since that is greater than equal to 1, right, some term greater than equal to 1, right, and this will be greater than equal to 1. And this is actually a very interesting step. Why? Because, oh my god, anyway, this is so annoying. That should have been like this, right? Excuse me for the typos. This is, I mean, technically that's not, but yeah, I need to write like this. Okay, I think if we change that, we're good only. Yeah. So yeah, that expression is, what was that expression? This is like greater than equal to 1, right? And then I am taking the power of theta, and then theta takes values between 0 and 1, right? So imagine like this is like a square root, or some quote-unquote generalized version of square root, right? And yeah, of course it will be greater than equal to 1, right? So let's look at again one more time square root function. This x, and then this is square root, right? So x, this is, what is going on? This takes values above square root, right? So this is greater than 1, and then I'm taking the square root, and then this is what we have. Okay, so alright, it will make sense. Seriously, it's like I understand. Just put some time, however you need to, and then it will make sense. Wait a sec. Now I think this is a very long and yeah, tedious explanation, but at the end what I'm saying is that we are proving that term greater than equal to 1, right? And that was the only term, like on the final condition that we need to prove the convexity of S1. So this is what we are doing. And so let's clean it and then look at it. Yeah, just look at it and then feast your eyes, right? So, and now this is like a controversial thing that I'm gonna talk about, and I'm gonna confess something. That was my instinction to make the following arguments, and hopefully in a couple of minutes I realized that was totally like wrong. But okay, I'm just explaining because I mean you can make errors like that, right? So okay, so now I'm going to show, you know what, everyone shows you how to solve a problem, and or how to make the correct arguments to solve a problem, and then I'm on top of showing that, I'm also showing what not to think about when you see a problem like that. So this is, I think, yeah, this is why you need to subscribe, right? Okay, so let's look at the problem one more time. This is the set that we would like to prove its convexity, and okay, so let's say this is x, right? This is x, and then this is set, right? And let's have some type of, this is my, again, like all the things I'm gonna say are, they will look scientific or mathematically precise, they will sound like that, but I am making a huge error, right? So be careful. Actually, try to understand, I mean, I am going to tell you about that, but try to understand what argument I'm making is kind of specifically wrong, right? That's not correct. You cannot do that, for example. And we have a one-to-one function, right? We can go from there and then we can come from here. And so I'm saying this x, right? And so this S1, and then let's call it this X2. So I would like to prove if that is S1 is convex. And if I have some type of transformation, like variable change of variables, and if, again, this is both y, because we have like yn, right? So if that's the case, and then I'm looking at S2, and if S2 is convex, then we can claim that S1 is convex. And this is only correct if that transformation is linear, if it is a linear map. If that is the case, then you can make that argument. If that's not the case, no way, Jose, right? So why? Because the best example is geometric programming. A given geometric programming, what was geometric programming? Like, I think it was something like this. No, wait a sec. I'm giving an example about geometric programming. I'm not even sure what that is. This is embarrassing. Let me write x1, x2, xm. Okay, this is alpha 1i, this is alpha 2i, alpha mi. So all those alpha terms, they are in real, and then this is crazy, by the way, right? But all those ci terms, I think they are, yeah, strictly positive. I mean, if they are zero, who cares, right? And so this is called, like, I don't want to look at that, but let's imagine, I shouldn't give like unnecessary details. Let's imagine this function. This function by no means is not convex. Like, that's obvious. However, by using, again, y equals, and these change of variables, and then after doing some like algebraic manipulations, we can solve this problem, this problem, like minimization of f of x, for example, like it's a convex problem in the change variables, right? In another domain. Let's call it like this is x domain, and let's call this a y domain. And in the y domain, this problem is convex. And here's the thing: the result that we can obtain in y domain is actually, like, this is the minimum, right? This is convex, and so we know that this is global minimum, and it's proven, like, way back in the day. Someone proved that it also corresponds to the global minimum of this function. So this is very important. What I'm saying is that although this is very interesting, I think, like, geometric programming is in and of itself is very interesting because of that fact. Why? Because this is not a convex function. F of x is not a convex function, like, end of the story. However, like, due to its structure, like, for example, ci terms being positive is like a very interesting, right? And very interesting, like, constraint. And then, of course, it's not satisfied all the time due to its structure, and we can look at this problem and then say, you know what, that I can solve it. So what do I mean by that? There are some certain sets of algebraic manipulations that I can conduct and then solve the problem as turn the problem in a convex way, a convex optimization problem, and then I can, like, if there's a convex optimization problem that is, like, solved, like you should be happy about it, and then you should say, yeah, this is convex, what do you want? Okay, I go home. Yeah, you can later tell your boss that. And so, however, again, in the y domain, this problem is convex, or this function, let's call it, this function is convex, but in the x domain, no, this is not convex. So what I'm trying to say is that why that is the case, how we were able to go from in the x domain that was not convex, and y domain this is convex. Why that was the case? Because this is not a linear transformation, right? So we are basically, so that corresponds to, imagine this set is something like this, and then due to linearity we are kind of bending that set and then turn it into a convex one. So this is in x domain, this is in y domain. So you can kind of kind of think like that, right? And you cannot make that argument. Yeah, I am in the transform domain and this is convex, and I know that this transformation is like bijective, right? And like this is like an isomorphism. You cannot make that argument. Only you can make that argument if that is a linear map, right? That is it. And so yeah, this is basic what I'm saying is that if you think about it, yeah, that is it. And then we can write this. So that is the case. I am taking the log of it, right? Actually, I feel like there's something wrong. Wait a second. Instead of this, I should have. Oh my god, there's a. Wait a second, is that correct? Like instead of xi, I should have written e to the yi. Okay, and then that corresponds to x of like I. Since this is e, wait a second, I'm taking b1, right? And then I'm taking the log, I think, log x, like log 1 is 0, and log, or rather like log, nature log x, this is what I'm saying is that, yeah, this is not, I mean, yeah, we can write it that way. Yeah, that will be easy to explain that way, but yeah, I wouldn't say that this is wrong. So okay, yeah, and then I'm saying convex in y, so don't make the arguments, right? Don't fall into that trap, and they're just trying to take your money. So wrong remark. Since the set in y variables is convex, the set in x variables must be convex. So this is a very long way of thinking. And remark, this explanation is not correct because the transformation is nonlinear, and that type of transformation can make non-convex sets appear convex in the transform variables. And the best example is that geometric programming, right? So I think that's it, and thanks for watching, and don't forget to subscribe.